Welcome to lesson 33, structure 3.1.8 HL lesson of my DP chemistry curriculum. In this lesson, we're going to be going over transition elements, talking about how their incomplete D sublevels give them their characteristic properties. So by the end of this, we'll be able to recognize properties including variable oxidation states, high melting points, magnetic properties, catalytic properties, and formation of colored compounds with forming complex ions with ligands. So that's everything we're going to be covering in this lesson. There's far more detail on it that will appear later as we talk more about this after bonding. But until we go through bonding, we're only just going to recognize the properties. So starting with what is a transition element? Now, we know we talk about the middle section of the periodic table as a transition metals, but a couple things that go along with that. So we know it's group 3 through 12 of our periodic table. We know we're going to learn at least that they can form variable oxidation. Didn't have enough room on this side, so we're just going to rewrite that lower. Variable oxidation states, which I'm going to start using OS to shorten that up just because I don't want to write it over and over. Now, variable oxidation states is when we're talking about ions like sodium forms a 1 plus ion, so it has one oxidation state. However, iron, a transition element, can be 2 plus or it can be iron 3 plus. So either work, and because of that, this is a transition element, this is not. So they can form variable oxidation states. And then lastly, and this is the important part, they have an incomplete D sublevel. So that's really important. Within that incomplete D sublevel, and because they have the incomplete D sublevel, they also form ions with incomplete D sublevels. So this tells us what elements are not transition elements. So for example, exceptions are zinc, which is not a transition element because zinc has a configuration argon 4s2 3d10. Because it has a full D subshell, this is not a transition element. So this is an exception to the group 3 through 12. It's in group 12, but it is not a transition element. So that's really important for us to keep in mind because specifically it is the incomplete D subshell or sublevel that provides these elements with their characteristic properties. So we're going to go over what those properties are and each of them and kind of explain it through. So property number one. The first property is that variable oxidation state, variable OS. So specifically what we're saying is that electrons can be lost from the S and D sublevels. Now, we talked about this before when we talked about electron configurations and becoming ions. We discussed how we remove from the S, then the D. Uh, but let's take a look at an example. So we'll take a look at the species will be iron, iron 2 plus, and iron 3 plus. The oxidation state for these are 0, no charge, 2 plus, and 3 plus, respectively, for their charges. But their configuration, we already learned this is going to be AR 4s2 3d6. And when it loses those first two electrons, they come from the S. So it just becomes Ar3d6. And finally, it becomes Ar3d5, having 5 unpaired valence electrons in the d sublevel. And that's what provides this variable oxidation state. It can become either of these, removing first from the S and then from the D. And that allows for iron to have multiple possible charges. The next property is that they have high melting points. So turns out this is also going to be due to those incomplete D sublevels and those high oxidation states or variable oxidation states. Due to oxidation states, they often have many delocalized electrons in their bonds. So the way the metals bond to each other is we have a bunch of cations floating around, and this is a metallic bond, and they have a unique lattice structure. And then we have little electrons floating around in between them, holding it all together. And the more electrons you have, the stronger that bond. The more delocalized electrons, which again are these guys, the stronger the bonds between atoms, bonds between, and these are technically cations, these little guys. So these cations are bonded to each adjacent one in their lattice via these delocalized electrons. And so the more electrons, the stronger the bond, and therefore a higher, oops, melting. Ooh, I fully flipped around the L and the T in melting point. If the bonds are stronger, it is harder to break those bonds. In other words, turn it from a solid to a liquid. So those are the melting point properties. We also have magnetic behavior. So it turns out those unpaired D subshells are the same reason. Elements with unpaired electrons can have magnetism. So with that, the more unpaired electrons, the more magnetism. Well, this is chemistry, and this is about all we really have to know. If you know a little bit of physics, electrons move. We even denote their movement or their spin when we're doing boxes, upspin and downspin. And those usually cancel each other out. However, if we just have one upspin electron, that will create a magnetic field. And because that's a spinning charges create fields, create magnetic fields, just like magnetic fields can create charge. And if you have a little bit of physics background, it starts to make a little more sense. But the more unpaired electrons you have, the stronger that field can be. And between atoms, these fields can line up, creating an overall magnetic field throughout the metal. So basically, the big things to know is this is caused by spin of unpaired electrons. This is about all you need to know in terms of magnetic behavior for the DP curriculum. There are terms like ferromagnetism, which means that it's inherently magnetic, and you do not need to know those terms, nor do you need paramagnetism or diamagnetism. Just know that transition elements can have magnetism, and that is due to spin of unpaired electrons, specifically in the D sublevel. So that is number 3. Number 4 are catalytic properties. Catalytic properties. Now, if you're taking biology, you probably know what a catalyst is. You may know about it from other examples, but basically, a catalyst speeds up chemical reactions. And the reason transition metals do is transition metals are a surface for reactions. We discussed in a previous lesson that reactions are just movement of electrons losing or gaining electrons, and due to variable oxidation states, of course, it's the same thing, they can gain and lose electrons to reactants in a chemical reaction. They can be like a holding place for electrons during a reaction, providing a easier pathway for two reactants to react. A great example of this is that in your blood and hemoglobin and heme, you have iron. We know that we need iron for our blood, and most people know it has something to do with the absorption of oxygen. Well, iron starts as iron 2 plus in the blood and binds with oxygen to become iron 3 plus, then reverts to iron 2 plus when oxygen is released wherever it has to go. So your body uses it everywhere. Um, we use it for our respiration. And once we have brought the oxygen where it needs to go, iron will let it go and revert back to iron 2 plus. And so it remains unchanged. Part of a catalyst, a very important part of a catalyst is catalysts remain unchanged throughout oh, throughout a reaction. So it can change during the reaction, but it must go back to its starting point once it has come back. All right. So that was number 4. We're on number 5. Formation of colored complexes, or colored, not complexes, compounds. So whenever you see things like stained glass or cool chemical labs where you see a bunch of different colors, usually those colors come from transition elements. So the color can change based on transition metal or even different oxidation states. So it's always the same thing. It's always going to come back to those different oxidation states. We're going to go in much more detail about this in a bit later after we go over bonding, like same thing as I mentioned before. So we'll come back to how the light interacts with the D levels to create these different colors, but that won't be for quite a few lessons. So for now, just know that one of the properties is colored compounds. All right. The last property we'll go to is formation of complex ions. This is also something we'll cover in more detail after we talk about bonding, which is going to be our next section. But basically, a complex ion, we got to know what it is going to have a charge. We know that because it's an ion, but it's an ion that has one or more species bonded to a central metal cation. So a central positive metal ion, it's usually going to be a transition metal. And this will be through what we call coordinate covalent bonds. We also just say coordinate bonds. You don't need to throw in the word covalent. We'll talk about those bonds more, but the important thing here is that the surrounding species, which we actually have a name for, these are called ligands. I'm going to highlight that one. Ligands are an important term to know and understand, but the surrounding species or ligands donates an electron pair to form the coordinate bond with the cation. And it's usually a transition metal. So what does this actually look like? Because generally we need some frame of reference, something visual. So you can take copper as a transition metal, a 2 plus transition metal. And if you take some water, water has two lone pairs, and we're going to put a few waters here. So this is going to take a little bit to draw, but we'll put 6 of them. And I could usually just copy and paste this. I don't know why I haven't decided to do that yet and just repeat the waters. But we're already here, so we're going to just keep drawing these. That's 5. Let's do one more. 6. So a covalent bond usually is the sharing of electrons equally. A coordinate bond is where those electrons are shared unequally, meaning that one atom provides both electrons instead of each atom providing one. So what's going to happen is both electrons from from the oxygen on one of those two lone pairs are going to be shared to create a bond with copper. And we get this structure that looks a little like this. Cu, OH2. OH2 is just shorthand for water. When you generally don't want to draw out all the bonds and you just kind of want to get the point across. On this side, I can put H2O. So I'm trying to be very clear that the bond is coming from the oxygen. And the whole thing has a charge of 2 plus. The reason for that is copper initially has a charge of 2 plus and water is neutral. And so even if you bond 6 waters, they're all neutral and the overall 2 plus is going to stick around. And that 2 plus charge is shared throughout the entire complex ion. So use these giant square brackets to denote that. So this compound is actually known as CuH2O 6 2 plus. So that's how we write our complex ion. And this happens mostly with transition metals. It can happen with some other elements, but mostly transition metals. A couple other niche things about this is we have something called the coordination number. Coordination number. And that's just a number of ligands bonded to a central atom, or more specifically, it's a number of bonds to a ligand from a central ion. So we talk about the coordination number of copper, not water in this example. So in that example, Cu has a coordination number of 6 because it has 1, 2, 3, 4, 5, 6 bonds. And there's a couple other common ligands you want to know. Common ligands. There's a few water clearly, but also hydroxide, also chloride, and also ammonia. Now, something to be careful about is that if we start looking at different charges or like maybe different coordinations, if you have Cu bonded to one hydroxide, another hydroxide, an ammonia, an ammonia, and let's say one more ammonia and one more hydroxide. Copper originally had a 2 minus charge. Now each hydroxide has a 1 minus charge, or copper had a 2 plus. So Cu, 3 OH minus, and 3NH3. The overall charge is 2 plus, 3 minus, and 0. Oh, that's a bad 0, and 0. Altogether, this has a charge of 1 minus. So when you have multiple ligands with different charges, you do have to take that into account when you are creating a complex ion. All right. There's two more uncommon special ligands. So some special ligands that form more than one bond. So the two special ones are ethylene diamide, diamide, which forms two bonds, and it's a ligand that can bond twice to the same compound, and EDTA, which can form 6 bonds. So this is pretty much everything you need to know about transition metals and their properties. I hope this helps, and have a great day.